So till now we have learned about classes, randomized verification, how pre and post randomized functions are used to set up initial settings. Now, in verification methodology, basically, you have, uh, as you have already seen in the previous presentations, that there are two very important blocks in verifications, and though they are called as drivers and the generators. Now, any from generator, if you see the literal meaning, it basically generates any value, and driver is the one which drives those values to the data. So in our case, you can see that any class can be considered a generator because we have this randomized bit variables, and then there is a virtual interface function, and this constraint is there. So basically, when an object will be created for a class ALU, so and that will be done through object.randomize, then in that case, you will have a set of variables, set of values for these variables, and that's why it is called a generator. The generator main purpose is to generate some value. Similarly, an interface declaration inside a class whose output is connected to the data inputs is called as a driver. So basically, what happens is that you have a driver, and the inputs of the driver, you have a DUT, and the inputs of the DUT are connected to the driver. In this case, we have the interface. You create a new interface, and after calling the randomize function for the object class, you just generate the traffic and pass it to the DUT. So you can see that in this case, the ALU interface dot one and ALU interface dot two are basically driving values to the inputs of the DUT, and it is expected that DUT will respond with some output, and that output will be taken care in the test bench, and we will see in the later part of this presentation that how that result is again manipulated or is again checked with different kind of output from the ALU functions. Okay, getting on with what are the scenarios basically in case of an ALU to check for which will entail all the verification aspects of ALU. We have till now covered classes, interfaces, modpods, and then we had driver and generator, and then we read randomized functions. So basically, we are done with the tools which we require for test bench development. Now we will see from conceptual point of view how a verification plan is created and how it is executed. So firstly, what happens that every verification requires exploring the corner cases of inputs. So in our case, like as I've already told before, like this is a DUT which is expected to have two input variables in which there are eight bits variables. So the corner cases can be anything from positive values, negative values, fraction, floating, divide by zero, integer values, so string values. So all kind of variables are possible, and it is mandatory to check how the DUT will behave if certain kind of values are inputted, and what will be the output if the DUT is given some spurious inputs or whatever in the case. So first is that whenever a DUT is provided to a verification engineer, he or she actually has to go through this specification which comes along with the DUT. So once that specification is read thoroughly, a verification plan entailing all the aspects of DUT are taken care of, and a verification plan is started out. Now, depending upon that verification plan, a test suite is generated, and that test suite will have some x number of test cases, which will generate some random values, and which will generate some random corner cases, which will generate some random scenarios, and those randoms are stress tested to on the DUT to see whether the output is coherent according to the specification. Once the output is produced, we see what are the results. If the results are coherent with the specification, then it's well and fine. But if it is not, then we have to see what are the errors. Are there any logical errors? Are there any syntactic errors? And hence the whole stress testing of that is done. So in case of an ALU, for example, we can see that what will be the output if suppose both the numbers are negative. If suppose both the numbers are zero, what will happen? If one of the number is either zero or negative, and or the other can be both the numbers can be FF, otherwise the output will cross 16-bit limit. So parameterized class testing, as I've already told, and extended class testing. So these are all the various scenarios in which an ALU DUT is supposed to go through, and once it passes all the tests, we can say, okay, yes, we are sure that this DUT is an ALU. Okay, continuing on to a next major portion of the presentation, we have is an inter-process communication. Now, as you have already read in the previous presentation, that in a verification methodology, you have a generator, you have a driver, you have a scoreboard, you have a monitor, you have a checkers. So they all are an integral part of a verification environment, and everywhere you need to have a specific data sets which have to be shared between different blocks. Supposedly, generator is generating some values, and that value need to be taken care of when it is passed to a scoreboard. Consider the example of a memory in which you are basically generating some addresses and some values, and you are basically feeding that memory with those addresses. Now once the write operation is done and a read is called, on the address which has been previously issued, then you have to check whether the data you have read from the memory is it coherent which with the data set you initially had. So this kind of concept is called a scoreboarding concept, and in this case you can see that you have to have that data which the generator produces, and you have to have all the data after the driver phase. Then you need to have the data after the driver produces the result. So at all these point, the data will taken care from all these three phases, and they have to be taken care of, and depending upon these data, you can have monitors and checkers. So in all these cases, you can see that in different blocks there's a communication which is exactly required. And in any test bench verification environment, this inter-process communication is a backbone of verifying strategies. So you can see that from introduction point of view, inter-process communication is a high level and easy to use synchronization and communication mechanism that are essential to control the kinds of interaction that occur between dynamic processes used to model a complex system or a highly reactive test bench. So in this statement, the dynamic process are the generation or the driving of generation of data, driving of data, or even scoreboarding of data. And a highly reactive test bench is one which actually passes on all the data to different blocks of verification environment. Example can be any two system communicating, like in the previous case, the generator might want to communicate with the driver or the vice versa, to see whether the data which it has generated and which has been driven to the DUT are equal or not, or whether any test bench has manipulated with those data or not. So these concepts are really important in case of data warehousing of information. So system Verilog offers variety of inter-process communications. They are primarily three. The first is mailbox, semaphores, and the events. So let us see how these are independently. So first we will go on through the mailboxes.